Virtual cylinder. Just to remind you, we're going to do the lab here with the cylinders, virtual cylinders. And two things that I always do so I don't have to go back and reconfigure I/O and channels and everything is I go up to Tools, Database, and I delete the database. This is delete the entire database. This is just delete the database for unused addresses. This is delete unused memory. So if I delete unused memory, it's going to show me how many elements that I have and what I'm going to free up. So I'm deleting unused memory, meaning that my logic isn't using anything. So you see, B3 was reduced by 2 elements. There were 3 words in there, and it won't eliminate all of them because it's going to leave one element of the array B3, T4, C5, R6, N7, and F8. So I'll just do that. And 73 words of data have been freed. So I'm going to close that. See, now I've got one word in B3. However, I don't like that. So I'm going to make everybody 10. Bump up to T4. C5. R6. It's doubtful we'll ever use more than a couple control words. N7, I think I might make that 32. That way I can emphasize that 31 is the highest value or last value if you have 32 something, 0 through 31. Okay, so just a reminder, Tools, Database. That deletes the entire database. That deletes just the database of unused addresses, symbols and descriptions. This deletes, it actually reduces the size of your data files down to just the words that you have used. Now, I will say this. If we'll go and do something here. I'm going to create a rung. See, it says file B3 cannot be reduced if I'm doing unused memory because I've used B39. I've used a bit in B39. So if you've used a bit in any element in your data files, you cannot reduce the size of that data file. However, you could change this if that was the only 2 bits that you used in this whole program. Now, that's impossible in a real program. You could go and change this to B31, we'll say. That way we're using a bit and 2 words with nothing in between them. Now if I go to Tools, delete unused memory, do a preview. See, B3 was reduced by 8 elements. Last used element, B3, 1, word 1. So I'm going to close that because I don't want to delete. Whenever you create a new project, or I say delete everything in the old one and just continue, what I'm really saying is that you need to delete, go to Tools, Database, and delete unused addresses or delete the entire data table. Don't delete unused memory. So this project right now has no database. In other words, there's no text on anything. But I have not lost my channel configuration. Channel 0 is still 38.4, and channel 1 is still 100, 100, 100, 226. I don't want to go back to a situation where I have to recreate everything. Once you've done it a few times, that's good. So delete Tools, Database, delete database, and delete your logic. You delete the logic database, now save it as the next project name. In this case it was cylinders, so I'll just call this and save it. Now that's just my scheme. You might want to shorten yours down to ML14 underscore cylinder underscore and not even use the page number. I'm just using this scheme in order to make it easier for me to refer back. Okay, I created a couple rungs of logic, and when I downloaded and went online, I had some bits on. Now these weren't bits that the logic turned on, these were bits that were left over from the last project. So if you want to quickly check to see if there's anything left on, go to Output, double click, change the radix to decimal, see right here, and they should all be zeros. Now it's going to look like this when you open it up. And you could go click on them individually. These three turned on. I look over at my digital field device simulator and I see 3 lights on. Well, if I popped it up and it looked like this, I could click on these one at a time and type in 0, or I could go to decimal and I see the value 28, because that's what those binary values would have been. 0, enter, and I've cleared them all. Same thing with input. You change it to decimal, and if there's any on right now, they would only be on in this word. I'll turn some on. Okay, now you can't clear those from here, but what it is, it's a quick way to see that you've got some switches turned on. So I go and I make sure they're all off, because a lot of times we're expecting you to start with a clean slate. No outputs on, no inputs on, nothing. And you see right here, the bits that we're using aren't even associated with inputs and outputs. Here's the first 2 rungs in the new lab on cylinders. And we're basically working with bit management or controlling bits. And I had you toggle this bit on, and you saw it flicker, but it didn't stay on, right? But it left this bit latched or set. Remember, this is a true only instruction. It sets B31 to a value of 1 or turns it on when the rung is true, but it doesn't turn it off when the rung is false. This instruction sets B300 to 0, if you like to use the word set, or clears it or turns it off. And this instruction has no idea who turned it on. So keep in mind, these instructions are dumb as bricks. This instruction only knows if a rung true out hits it, it sets that memory location pointed to by B31, it sets it to 1. This instruction, when it has a rung true that hits it, it turns that bit off in memory. It sets it to 0. That's all it does. It doesn't know who turned it on or how it got turned on or when it got turned on. It just, carte blanche, just goes and either sets it to 1 or sets it to 0. So we toggle on this bit. I'll toggle this one back off. I'll toggle this one on again. And remember that these instructions always show on-off for the memory location. These show true and false for the instruction as it relates to the memory location. What we did here was we used this instruction to turn this back off. So otherwise we would right-click, toggle bit, right-click, toggle bit to get it to go on then back off. I'm sure you've figured that all out by now. And if I do the same thing here, I toggle this bit, it unlatches or clears both these. If I toggle that bit on, this latch sets that memory location to 1 or on, and this sets this back to 0. There is only one bit on here. We only have one latch instruction, B30/1. These are all unlatches. So I do this, it clears B31 and it clears itself. This is very typical in bit control, is to use the unlatch instruction to turn off a bit for any reason that you want. Do we have to latch a bit on before we can unlatch it off? No. The OT instructions have a true execution to set the bit to 0, or turn it off if you like. And it has no idea of who or how it was on, or even if it was on. Okay, this bit right here, B301, is it on or is it off right now? It's off. So if I toggle this bit, it went true, you just couldn't see it because this cleared it within a thousandth of a second. But this instruction just told this memory location to be off. Well, it wasn't even on. So this, you got to keep this in mind all the time. Otherwise, you're going to misunderstand logic. To unlatch something, you may think implies that it was latch. No, it just tells it it's 0. If it's already 0, who cares? It just tells that bit in memory, hey, you're 0. This one says, hey, you're 1, you're on. This one says, hey, you're off, you're 0. That's it. Our 2 rungs here that we added, if we toggle this bit on, we're going to set that bit. I'll toggle that back off. So we're looking at it in the fresh format. Nothing is on right now. No bits are on except for input 1. Now you're saying, well, I don't see it on. Well, it is on because this instruction is false. True if off, and it's not true, it's false, therefore the bit is on. So we've got the sensor for the retracted position of the cylinder turned on to simulate the cylinder starting in the retracted position. Now if we initiate the cycle, and that turned itself off, now we've turned on this permissive that's going to allow extend and retract. However, the next thing that's going to happen, that the cylinder is moving, and it's moving off of the retracted sensor. So what's going to happen next is not what we want to happen, but this is logically how you work your way through these things. You have logic that says if it's not extended, then extend it. If it's not retracted, then retract it. The problem is when it's in the middle, extending and retracting, in other words, it's not extended right now, right? It's retracted. So I'm going to turn off the retracted switch. Input 1. Remember, I can't turn on input 0. So right now it's actually in the middle. It was in the middle of a motion. It left the retracted sensor, but as soon as it did, then it told it to retract. So right now both solenoids are on, and that typically will burn up a solenoid. If you energize both solenoids, the spool may be stuck in the middle, and with no core pulled into the solenoid, there's too much current. There's not enough counter EMF to limit the current in that coil, and you'll burn the coils up. Now in the manual, I have retracted still on. Notice in the image, this is what you're looking at. And the questions say, in the online state, the logic to the left, is the cylinder retracted, extended, retracting, extending? The answer would be yes, it is retracted. Is it extended? No. That's based on input 0 and input 1. Input 0 is off, therefore it's not extended. Input 1 is on, therefore it's retracted. Is it retracting or extending? No, it's not retracting, but yes, it is extending at that instant. But keep in mind, the position of the piston, even though it's starting to move and extend, it hasn't left the retracted prox or position switch yet. So it's still extending. It says justify your selection in the previous question. Well, I just explained it. Then in the manual, I had you flip input 1 to the off position to simulate it going off of the retracted prox switch. And here's the problem. And it's stated so in the book. It says, okay, in the online state of the logic to the left, is it retracted? No. Is it extended? No. Is it retracting? Yes. Extending? Yes. Now, you could have answered that, all of them no, because you might want to argue that if both solenoids are on, then it's not doing either. Chances are one came on before the other, so it may be extending for a little bit or retracting for a little bit. So how you answered this is not really as important as whether or not you understand it. With this logic, what will the rod be doing? Nothing. It'll be stationary because the two solenoids are going to balance out. Now, if there's always a chance, depending on the quality of the valve and type of valve, solenoid valve, that because you did hit the extend first, in other words, you told it to extend, output 1, that may have shifted the spool all the way into the coil inside the solenoid, and then that increase in magnetic flux density is going to hold it there. So then when the retract solenoid, output 2 energized, the spool stayed right where it was at, and so it continued to extend until it got to the other end, and then it would clean itself up. So if I were to turn on the extended bit right now, in other words, input 0 goes on, now it's going to retract. And as soon as it comes off of the extended, it's going to do the same thing until it hits the retracted. So it is possible that it will cycle, but this is not really the best way to do this. You never want both solenoids on, not even for an instant. Next, we showed you this logic, or I should say state of the logic. What you should notice right away is neither solenoid is turned on, but both of the proxies are turned on. Cylinder A extended and retracted, they're both on because both those instructions are false. And then the question was, can this state ever exist? No. Why? The cylinder can't be at both ends at the same time. In other words, you can't have both proc switches on. It cannot be extended and retracted simultaneously. The question that we asked was, what conclusions might you draw regarding the physical devices themselves in this particular state? The answer would be both off during motion is normal. Okay, if they were both off, like this, and of course we don't want both solenoids on at the same time, but ignore that for a minute. They're both off right now, and that's why both solenoids are energized. That's normal. But both on at the same time? No way. Not unless one of the sensors is shorted or bad. The important takeaway is that both sensors can be off at the same time because they will be off during motion, but they can never both be on at the same time. When you write code for solenoid valves, you have to be careful to consider the type of solenoid design that you are energizing. Some can be continuously on, and others have a very low duty cycle, and they can only be pulsed long enough to shift the valve, and then they detent, and they're held there by a detented physical force. And if you want to go the other direction, you energize the other solenoid momentarily long enough to get the spool to shift, and then it's right back off. So it's a momentary energizing of the solenoids to get them to go back and forth, then they're detented in the position. And that's the reason why we went through and kind of discussed solenoid valves and cylinders a little bit, to make you aware that there are single and double solenoid valves. A single solenoid valve is going to have two positions for the spool. One of them is attained by powering, applying electricity to the coil, and it shifts the spool. And then when you de-energize it, a spring pushes it back. And then with double solenoid, you can pull it to one end or the other, and if they're both turned off, its spring returns to center. So there's maintained in one position or the other, and there's also spring return to center, which would be 3 positions. And in that center position, it can be all ports blocked or not blocked. You really need to have a little background with the solenoid valves and the spools and the symbols if you're going to work a lot with pneumatic control. So then we kind of ask you, how could you fix this logic or add some to prevent it from turning on both solenoids simultaneously? Right you are. We're going to add an instruction on each of these 2 rungs that says extend it if you're not telling it to retract, and retract it if you're not telling it to extend. So we'll exercise our logic here and see if this cleaned it up somewhat. So I'm going to initiate a cycle. And remember, when I initiate the cycle, it's based on the current position of the cylinder. Where is the cylinder right now? You can determine that by looking at these 2 bits. Now remember, this one is off and this one is on because these are true if off. So that means that it's retracted because this bit is on and this instruction is false. So if I initiate a cycle, it should extend. And it does. Now, the next thing that happens is it comes off of the retracted proc. So let's change the state of input 1, turn it off, and you see nothing happens. It's still extending. And it keeps extending until it turns on the procs at the other end, which is the extended proc. So we'll change the state of that. And you see now it's retracting. and it will retract until that is on. Okay, right now the retracted. The extended is going to go off as soon as it starts retracting. But that doesn't interfere with the retracting. It continues to retract until that input comes on. And now it's going to extend again. So basically, this logic, the cylinder will just sit there and go back and forth between extended and retracted unless we have a cycle complete that unlatches the cycle cylinder once. We don't have a cycle complete in there. In this state right here, this was shown in the manual. In the online state of the logic to the left is the cylinder retracted. With input 1 on, which it is, you would have to say yes. Extended, no, because input 0 is off. Is it retracting? No, because input 1 is on. Is it extending? No. So yes, no, no, no. Now you may need to think about that. Remember, we're using input 0 and input 1 to simulate our cylinder position switches, but we're operating them by hand. Later on, maybe we'll add code that uses timers to simulate the motion. If I'm extending cylinder A, I'm going to turn off the retracted. And the logic, this logic is shown in this state in the manual. It says in the online state of the logic to the right is the cylinder retracted. Well, you look at your two inputs, input 0, input 1. Those are both true if off, which means if they're both true, then both of those are off. So it can't be retracted or extended. If it's off of both sensors, input 0 and input 1, then it is neither retracted nor extended. Is it retracting? Well, look at your outputs. The retract solenoid is not on, so it's not retracting. And you look at your other output, the extend solenoid, it is extending. So if output 0, 1, extend cylinder A solenoid, if that's on and neither sensor is on, meaning the piston's not at either end, then it has to be moving in the direction of the solenoid that's energized. So it would have to be extending. So you look at this logic right here, and you can say that the cylinder is extending. So I could add a rung of logic that says if neither input 0 and 1 are on, in other words, true if off, input 0, input 1, and output 1 is on, in other words, true if on, in output 1, then I could create another bit, not seen here, that would be have a symbol or text on that says cylinder A extending, meaning that it is in the process of extending. At some point, we're going to hit extended, right? So that's going to go on, and now that rung is false and the other one is true. And we show that in the manual. In the online state of the logic to the left is a cylinder retracted. No, because that input 1 is off. Now, we could say it's extended because input 0 is on. So it's still extended even though we got the retract solenoid energized. But that's just for an instant. Is it extended? Yes. Looking at the logic, it's extended. Is it retracting? Yes, because it can be in motion and not off of the prox yet. Is it extending? No. So no, yes, yes, no. What is the very next thing that will happen? The very next thing that will happen is that it will be moved completely off of the extended prox. So we'll do that. We'll turn input 0 off because the cylinder is retracting off of the extended prox. So this is the next logic, state of logic shown in the manual. Is the cylinder retracted? Well, we know it's not retracted or extended because both of those bits, input 0 and input 1, they're off because those instructions, true if off, are both true. So it's not retracted and it's not extended. Is it retracting? I'd have to say yes because that output is on. Is it extending? No. Don't split hairs on the retracting or extending business. The fact that it's off of both input 0 and input 1, in other words, neither sensor end to end is on, therefore it's in motion somewhere in between. So you could create a bit here that says if both sensors are off and the retract cylinder is on, then right now it is retracting. You could have a bit that's only on while both sensors are off and the retract solenoid is on, and that bit would be true only when it's retracting. And you could have another one, which we described before, that would only be on when it's actually extending. If the cylinder is retracted, eventually it will reach the end of stroke, or more importantly, the retracted sensor will sense the piston. Change the state of that sensor. So I'm going to turn on input 1 to say that it is retracted. Of course, immediately it wants to extend. So what is the cylinder doing? Extending. Left as is, what will the cylinder do? It'll cycle back and forth from one prox to the other, one sensor to the other. Well, keep in mind that those sensors are physically adjusted. They normally fit in a slot. So you can have them so they just barely come on when this, and I don't know if I mentioned it, but cylinders quite often have a cushion. The rod that moves back and forth, it has the ability to reduce the compression area to a real small area to go into a cushioning mode. Meaning when it gets, 90-95% of the distance, then the airflow is restricted to slow it down. So it's called a cushion. Now, when you adjust those sensors, you can adjust them so they go on as it hits the cushion or when it gets to the end of the cushion. When it hits the cushion, there's still a little bit of motion left. Also keep in mind that these sensors have hysteresis. Meaning, if you sneak up on that sensor, in other words, if you're operating the piston by hand, you're just slowly pushing it up there until it turns on. If you mark the point linearly where it turned on, you're going to have to back off past that point to get it to turn to switch state. It's called hysteresis. In other words, if you're in motion, the point where it turns it on is not the point where it turns it off going in the other direction. There's a slight difference. So you need to be aware of hysteresis and adjust your sensors accordingly. Well, we don't want the cylinder just sitting there cycling back and forth. That's useless. We want some control over it. We are making it travel between the two sensors, extended and retracted position sensors. So I had you use another input 5, and use it true if on in one rung and true if off in the other. Then I ask you the questions. In the state of the logic, is the cylinder retracted? Well, look at the input 0 and input 1. Input 1 is obviously on, therefore it is retracted. Is it extended? No. Is it retracting? No. Extending? No, because neither solenoid is on. So the logic is now stationary and awaiting a change. I had you operate this logic, so input 5 is a toggle switch. I'm going to flip it. We start extending. The first thing that's going to happen is we're going to turn off the retracted sensor because it's in motion, and then turn on the extended. In other words, it's extended now, and it just sits there in the extended position. Now if we flip input 5 back to the other position, now we're retracting, and the first thing that happens is we move off of the extended prox, and then eventually it hits the prox on the other end and turns that prox on. Now we're sitting there waiting for something else. So input 5 now is extend retract. Now I'm using a toggle switch for input 5, but it could be a push button. What we don't have here is an easy way to turn input 0 and 1 on and off based on our motion. In other words, we have to keep track in our heads of, okay, now let's see, true if off, okay, that means right now, let's see, true if off, input 0, that's true, okay, that true, okay, then it's on. And then do the same thing with input 1. Now that is a bit of a nuisance, working with true if off and keeping track in our heads of the position of the sensors, but you're going to have to get used to this. This is just how the logic is written. What I didn't do in the manual, why I'm not sure, I must have forgotten when I was writing it, but we never used the cycle complete bit. So let's go back and consider what we could have done there. So I'm going to take out my toggle switches, And I'm going to use the cycle complete bit. I'm going to turn it on when the retracted procs goes on. I'm going to one-shot it. Okay? Now we have to one-shot it because remember, we're starting retracted. We want it to extend, and then when it comes back and hits the retract again, we want the cycle to be complete. Perfect use for the one-shot. So I'll use 14. And I'm not going to bother putting any text on it. I'm going to do two things here. First of all, I'm going to finish the logic as I described it. Now I'm going to select this rung, Control, Control, and do all three of them at once. Okay, so now we are not extended, we're retracted. So let's do this, see what happens. But we still got to operate our switches, right? So we turn on the extend solenoid, so the retracted is no longer on. So we turn that off, and then eventually we hit extend. Now we tracked it. We turn off the extend, and we return on the retracted, and see it drops the whole thing out. Now you might want to sit and play with that for a while. That's where I meant to go with the cycle complete business, and it just never got into the manual. Next step, and I said we no longer need cycle control rung 0, and in the manual it might have said 0 and 1. Well, looking here, that wouldn't work out very well. Basically, I meant 0 and this rung, but then we added this rung as well. So we no longer need anything but these two rungs. So you deleted all the rungs but these two. A lot of what you do with PLC programming or PAC programming, ladder logic diagrams, is you are working with a virtual process, or rather a data framework of a process. If you look at any given process that has things that move, like cylinders, each cylinder has a specific behavior that's initiated by an extend or in a retract. So if you put some dynamic characteristics to that, or specifications, that's how you end up doing your programming based on your knowledge of those specific dynamics. So what we've done here is we've added two rungs of logic. They are identical, one for extend and one for retract. When we energize the solenoid to extend a cylinder, there's going to be a little delay between when you turn the output on and when the cylinder actually moves. So T40, retract switch off delay. What we're doing is we're delaying the retract switch, the proc switch, changing state or going from on to off for 1 second. And that simulates that, we'll say it's probably less than 1 second, but we're going to make it 1 second so we can observe it. From the time that your logic turns on the bit in memory that O:0.0/1 points to, from that instant to when the cylinder actually pushes the piston away from the retracted switch or sensor, we're saying is 1 second. At the end of that 1 second, then we're into the extend interval or the extending interval. It's probably better to, I put extend interval, but it could be extending interval. When it comes to grammar and verbs, it's good to get as close as you can to what you're actually describing. The 1 second delay to move off of the retract switch, and then we start a 3 second interval, and we're saying that that's how long it takes to get to the extended switch position. For now though, we're just creating these two motion profiles using the timer. The second one, retract cylinder A, solenoid, when that energizes, we're saying it's going to take 1 second to get off of the extended switch, and then another 3 seconds before it reaches the other end. That's all this logic does. And of course, we don't show any use of the bits. We cascade the two timers together, T40 and T41, using the done bit from T40. You've done this before, only you were blinking lights instead of simulating a cylinder. Believe it or not, there is a lot of logic written like this to simulate elements in a process, part of something called a FAT, or a factory acceptance test. And this is where you actually run the process without having the physical process. So you have to write code to simulate the reaction to any actions you take. In this case, extend the cylinder or retract the cylinder. These two rungs we added to the bottom of our code. Let's go back up to the top. These are the 4 rungs that, actually the top 2 are the remnants of what you did previously. These are the rungs that turn on output 1 and output 2, extend and retract the cylinder. We've replaced the cylinder A extend procs and cylinder A retracted procs with internal bits, B320 and B330. Remember, this used to be input 0 and input 1. We no longer want to use toggle switches to simulate the end of stroke on the cylinder with the position sensing sensors, the proc switches. We want that to be a reaction or a bit associated with those timers down below. But we still have the extend and retract switch to get extend and retract. And we're going to do some logic here that uses bits from the timers to complement the bits that we're using to simulate the extended procs and the retracted procs. In parallel with that, we put outputs 0 and 3, so you can actually see lights come on your digital field device simulator to indicate when those procs are made. If we had a cylinder sitting right in front of us and we could see both sensors and the LEDs on the sensors, this would be so much easier to visualize. But we're looking at the code, and we have code here to simulate that cylinder motion. Right now we're offline, so I'm going to save this and then download it. So now let's run it. Right now you see that neither of these rungs are true, so we're not extending or retracting, and our condition is such that it says we're in the retracted position. And we have a light on our digital field device simulator. So I'm going to flip the switch on, and that switch is input 5, that's the bottom toggle switch. And I'm going to flip it on, and you see it said to extend, and now it's extended. So notice that all happens so fast. What we're watching is the extend cylinder solenoid, and we're watching the extended procs. Now we're going to go the other way, so we should see the retract come on, and then after those timers time out, then we'll see the retracted procs. But you'll see this go off within 1 second, and then 3 seconds later this should come on. So I'm going to turn off input 5, retract, retracted, extend, extended, retract, retracted. The only logic here that actually runs the cylinder are these 2 rungs right here. If you're not extended and you're not retracting and you flip this switch on, then it's going to extend, as you can see there. So we saw this go on when it reached the other end. Now both these rungs are false. If you pretend that these 2 bits right here are actually inputs from proximity switches, that's all the code there is, or these 2, rung 0 and rung 1, that's it. All the rest of this does nothing but simulate the dynamics of that cylinder. And being able to write a program that simulates any portion of your process is a good thing, because you have to really understand the process to write code that simulates its dynamic behavior. Now we're going to add code to monitor how long it takes the cylinder to extend and how long it takes to retract. Now you notice from the logic here that the extend solenoid only stays on until it reaches the extended procs. The retract solenoid only energizes until the retracted procs is made. We put 2 timer instructions, 2 TON, addressing 2 new additional timer data types in memory. And notice that our elapsed timer, our preset, is 4 seconds. So that would be the sum of the two timers that simulate the motion. Let's see what it does when we make it equal. It takes 4 seconds. If this is on for 4 seconds, will this be done before this goes off? Of course, we have no way to capture that, but let's see if, the question in the book was, do either of the timers time out and set the done bit? Well, let's go ahead and operate that. So I'm going to extend. There's no way to know if T44 was done or not, because the sum of the two motions, or we'll say the just getting off of the sensor and then the travel time, that adds up to 4 seconds, and we got a preset here of 4 seconds. If I made it less than 400, then I would know for sure that it was timing out. We don't actually want it to time out. So if we wanted to see if the done bits were set, we would have to put in some way to trap that bit to see if it was actually staying on that long. So now let's retract, and you see now the solenoid is on for 4 seconds in the other direction. All that we've established here is that we have a timer data type that has a timer timing pulse, the length of time it takes to extend, and the length of time it takes to retract. That's all we've done so far. Do either of the timers time out and set the done bit? I would say, because they are at the top of the code, in other words, these timers are further down below, so these are going to time out after this timer times out. So I'm saying no. As long as you understand what we're doing here, we're good, whether you answered yes or no. By looking at the logic for the virtual cylinder, what is the length of interval that each motion requires before it sets the sensor's bits? Well, 4 seconds, because you have to include the time it takes to get off of the sensor and then the actual visible travel time. It says drop both proximity switch off delays to 75 hundredths of a second. We go down to here, and we're going to bump these down to 75 and run this again. Extend. Now we know for a fact that it did not set the done bits, because our timer T44 and T45 is 4 seconds, and the total length of time now is 3 3/4 seconds for the cylinder motions. Then I had you increase the actual travel time to 350 on both. We had you increase your extend and retract interval to 350. Now remember, this is the interval that we're simulating, not that we're measuring. We're not measuring the interval, but these two rungs right here simulate extend and retract for the cylinder. So this logic replaces an actual cylinder. This is not logic that controls the cylinder. It's our virtual cylinder. The amount of time it takes to come off of the sensor, and then the amount of time it takes to get to the other end. That's all this is. So we bumped it up to 350 to see what happens with our logic. This is the actual logic right here that measures how long it's taking to get to the other end. And remember, this is the total combined time, because it's that logic that determines how long we leave on these two outputs, extend and retract solenoids. So let's flip our switch and watch to see if either of these timer data types time out. You saw the done bits come on. Now they didn't come on for very long, but you see the done bit did come on. These two timers are actually measuring the motion, and if it exceeds a certain length of time, then we want to declare that there's a problem. So the answers in your manual would be to the question, do the done bits for both T44 and T45 get set? Yes, they do. Which? Both. For how long? 1/4 of a second. You didn't observe 1/4 of a second, you just saw it blink on then right back off, because remember, when the rung goes false, that resets the timer data types that are being addressed by TONs. If you wanted to verify that a bit was on, even for an instant, what did you learn in a previous project that could capture or trap that instance? Using the OTL instruction, In other words, latching the bit. At the tail end of that lab, we had a question. Do all the timer instructions have both a true execution and a false execution? The answer is no. Elaborate on each of the instructions. The TON, the TOF, and the RTO, if the run goes true, they're enabled. Okay, so the enable bit behaves the same regardless, but no one uses the enable bit for anything in code. The TON and the RTO are both on delay timers. The difference between a TON and an RTO is the false execution. The TON's true execution is whenever it receives a rung true condition, it enables the timer data type to start counting units of time. The enable bit, of course, goes on immediately, and then the timer timing bit is on while it is accumulating, and when it's done accumulating, the timer timing bit goes off, the done bit comes on. The RTO behaves basically the same way. The difference is it has no false execution. So nothing's going to reset it short of using the reset instruction. The TOF is the oddball. When it's done, it's not done, and when it is done, then it's not done anymore. I'm referring to the done bit. When you enable it, it's done until the run goes false. Then the timer starts timing, the timer timing bit is on, and then when it times out, the done bit goes off. So you're actually transferring the function of whatever makes the run true to the done bit, and the done bit is the off delay that you're working with.